Hey y'all, my name is Mr. Canada and welcome to my math domain. In this video we're going to be talking about simplifying radical expressions using the factor tree method. Now there will be another video about how to simplify radical expressions using the perfect square method, so if you don't like using the method presented in this video, I will present another way that you could do these problems. But let's go ahead and get started. So what's the idea behind simplifying radical expressions? Well, to start off, let's go ahead and talk about what a radical expression is. So a radical expression is basically any kind of an expression that contains this symbol, what we call the radical, which you might know it as the square root symbol. Now there are two pieces to this. So with every single radical expression, there's two parts. There's the symbol itself, which we call the radical, and then there's a number on the inside, which we call the radicand. So I'm going to go ahead and put that as a big vocab word there. That's going to be called a radicand. The number on the inside is called a radicand. The symbol on the outside is called a radical. Now, mainly in the scope of an Algebra 1 class, we're mainly going to be talking about a very special kind of radical, basically a square root symbol. Now, whenever we're talking about square roots, we're really talking about radicals with an exponent of 2. Okay? So, what's the big idea with this whole video? Like, what's our goal? What's our ultimate goal here? Well, our ultimate goal is that we want to simplify expressions that contain numbers like these. But we want to look at a very specific kind of radical expression. Let me present to you this example right here. Let's say that they asked us to simplify the square root of 4. Now, if you're a numbers wizard or you have a calculator and you try to go ahead and think about this, you might end up getting an answer of 2. Now, if we present you with the problem of, let's say we take the square root of 9. Again, for all you number wizards out there, or if you're not sure and you used a calculator, you're going to get a whole number of 3. Now, let's say that you take something like what's down here, you take the square root of 8. Now, you number wizards might actually have a problem here because you're thinking, well, I don't think this is going to be a whole number. And then if you check this on the calculator, you might get that the answer is 2 point blah, 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 blah. Now, why did these two end up giving us a whole number answer, but this one ends up getting us a decimal? Well, the reason for that is because 4 and 9 are what we call perfect squares. And basically what a perfect square is that it's a number that consists of a different number that when you multiply with itself, you get that result. In other words, if you multiply 2 times 2, you're going to get the whole number of 4. That's the reason why 4 is a perfect square, is because it consists of 2 whole numbers which multiply with itself will get you a nice whole number. Same thing with that 9. If you multiply 3 times 3, 3 with itself, you also get a whole number of 9. So that's the reason why you end up getting such nice answers for these. But if you were to look at something like 8, you're basically trying to answer the question of, well, what number can I actually multiply with itself that'll get me, well, 8? And that's the question that we're trying to answer today. It's how exactly can we obtain a number like that, such that when we multiply it with itself, we'll get that whole number of 8. Now, why can't I just multiply the 2 decimals that I got before? Well, if you try to do that, you're not going to get a whole number of 8. If anything, you'll be a little bit under. What we're trying to shoot for here is an exact answer. And that's the whole point of this video, is how exactly can we get an exact answer out of every single one of these. Let's go ahead and find out. So, what's the strategy here? Well, as the video entails, we're going to go ahead and simplify these using a factor tree. So what is a factor tree? Well, if you remember from a factor tree from one of your previous math classes, basically the idea is that you're going to take the number that's given to you, and you're basically going to make all these little tree branches of numbers. And you're basically asking yourself, well, what 2 numbers multiply to get me the starting number? In this case, you can pretty much say whatever you want. Well, in this case, you really can't, honestly, because it's just 2 times 4. I mean, you could say 8 times 1, but that doesn't really help. So, the biggest thing you have to remember about a factor tree is that you have to stop the branch right at the prime numbers. What's a prime number? Well, a prime number is a number that can only be multiplied with itself in 1. So some of the classical prime numbers would be like 2, 3, 5, 7, etc. You can look up a list online. So basically this is where the branches of every factor tree should stop. So in this case, the branch on this side is going to stop because we have a prime number of 2. But this 4 is a composite number. Basically, we could still split that up into 2 times 2. Now, why is it that we can't just say, oh, why can't we just say 2 times 1? That's still splitting it up. And you're right, you wouldn't be wrong on that. But here's the thing. If you're splitting that off into 2 times 1, you're just creating more branches that aren't necessary. Because I could just say, hey, I could just do 2 times 1, and 2 times 1, and 2 times 1, absolutely everywhere. But if you multiply all those numbers, are you really going to get back the number 8? No, if anything, you're going to get like a really, really huge number. So you don't want that. So always stop at the prime numbers if you can. So at this point, we pretty much finished our factor tree because all of the n bits, all the branches are prime numbers. So what's the next step? The next step is that you're going to replace the number 8 that was in the square root with all of the prime numbers that you have. So in this case, we have 2, we have another 2, and we have another 2. Notice I'm not including that 4 because that's not a prime number. So what do we do with all these 2's? Well, the idea is going back to the idea of the perfect square, is that you want to go ahead and try to circle the number with itself. In other words, notice that I'm always doing pairs of the same number, and that's exactly how we're going to go about simplifying this expression. I want to create as many pairs without any overlap of this example. In other words, I can only make a pair right here. I can't say that this is another pair right here because there's an overlap. That one of those 2's is already being used, which is not okay. So we can only make one group here. Okay, so I made my pair. Now what do we do after that? For every pair that you circle, you're going to cross that pair out and you're going to take out a 2. Or you're going to take out that number. For any numbers that you didn't circle, they're going to remain on the inside. In this case, since this 2 right here did not get circled, it's going to stay on the inside of my radical. This right here is my exact answer to the square root of 8. That means that if I were to take this and I multiply it exactly how I see it into a calculator with itself, I will get an exact answer, a whole number of 8, which is pretty awesome. So what's the idea? The idea is simple. You're going to take this number, you're going to make your branches, you're going to split it up, make your factor tree, stop when you have prime numbers, put your prime numbers on the inside, and then start circling your pairs. Let's go ahead and see if we can simplify the square root of 72. So in this case, I'm going to go ahead and start my branches. Now here's the great part about this. It doesn't really matter how you go ahead and start the splitting off of 72. There's a variety of options that you might have. And if someone chooses a different method that you do, that's okay. For example, one of the ways that you could split off 72 is just saying 9 times 8. Another way that you could do it is saying that it's 2 times 36. What's great about this is that no matter how you start, hopefully if you follow through with your divisions and your simplifications, and with the occasional double checking on your calculator if you're not sure, you could always have the same answer at the very end. So let's go ahead and see that in action real quick. So I'm just going to keep it safe and split 72 in half because I know it's even. So for example, 2 times 36 will give me 72. I can split off 36 into 2 times 18. I can split off 18 into 2 times 9. And I can split off 9 into 3 times 3. So we're going to go ahead and do the same thing. We're going to go ahead and circle all of the prime numbers that are given to us. In this case, we have a new type of prime number that's given to us in this problem, and it's the number 3. Now, we're going to go ahead and open up our radical sign over here. Now remember, we're going to go ahead and just put these numbers here. We're not going to put 36, 18, and 9. Those are not prime numbers. So 2, 2, 2, and then we have a couple of 3's in there. Now, same kind of idea. You want to circle pairs of the same number. What's different about this problem is that we actually have a pair of 2's and a pair of 3's. So could your pairings be different? Absolutely. Just keep this in mind. If I'm going to cross off this pair, I'm going to take out 1, 2. If I'm going to cross off this pair, I'm going to take off that 3. We're always taking out whatever the number is in the pair. And whatever is not circled is going to stay on the inside. Now, it's not a good idea to keep your answer in this form right here where it's just 2 times 3. Follow through with the multiplication. 2 times 3 is just 6. So our final answer would just be 6 square root of 2. So what should you do in case that you have two different pairings? Well, just keep going. Just make sure that you take out one of those numbers. for every pair. It's nothing too much different. Now, what should we do if, let's say, they give us a radical with variables in it? Does our strategy change? Absolutely not. If anything, let me show you a nice and easy way that you can approach these types of problems. So, what's going to stay the same? What's going to stay the same is this. What's staying the same is that our strategy, our game plan is going to stick. So that means we're going to go ahead and split off that 20. 2 times 10 can be 20, and then 10 can be 2 and 5. Again, we're just going to keep it super simple. We're going to keep the same game plan that we've always had before. So 2, 2, and then 5. Now, how do we actually start including these variables right here? Well, this is what you have to recall here. Recall what an exponent actually tells you. An exponent tells you how many times you're going to multiply that number with itself. In this case, x to the power of 3 could be written as x times x times x. Basically, x multiplying with itself 3 times. Now, the beauty of that is, once you have those 3 x's, you can pretty much copy them right here. Now, why is this any better than what we had before? Because it's easier to make the groupings this way. Because now here, I can say that we have a group of 2's, and I can also say that we have a group of 2 of x's here. We have a pair of x's. So that means that I'm going to take my 2 out here, I'm going to take an x out here, and I'm going to leave anything that I did not circle on the inside. I leave a 5, and I leave that x on the inside of my expression. So my expression is 2x square root of 5x. That's how we're going to start tackling these variable problems. We're going to keep it simple. We're going to split it off. So with this one right here, we're going to start with splitting off 50. 5 times 10. Here we can say that's 2 times 5. So radical 5, 5, 2. I'm going to go ahead and go back and circle my primes. Now here, let's go ahead and create some space so we can include all the x's. Here I have 5 of them, so that's 1, 2, 3, 4, 5. And again, ask yourself how many pairs we can make. We can make 1 pair here, we can make 1 pair here, we can also make a pair right here. So, what's going to happen? Well, I take a 5 out, a 5's on the outside. I take an x out, x on the outside. I take an x out one more time, another x on the outside. Whatever I did not circle stays on the inside. There's a 2 and an x on the inside. 2 and x. Now, just like in the previous example with the 2 times 3, we don't want to leave it this way. Don't leave it as x times x. Simplify. Turn it back in an exponent form. So 5x squared times square root of 2x. So what's the idea here? If you have variables in your problem, go ahead and write them all out so it's easier to make your groupings. I hope you guys learned something new today. If you have any questions, please let me know in the comments. And like always, please take care, and I'll see you guys next time. Peace.